Okay, our next topic is transmission and speed of sound. So what's the goal today? I want you to be able to explain how sound is transmitted through a medium and how real-world applications like Mach number are connected with the concept. So you have the note in front of you. Sound. Sound is a longitudinal wave. All right, longitudinal wave. So when we speak, okay, our diaphragm compresses the air in our lungs that travel out through our throat and so on, so that it travels in this format. All right, so sound travels as a series of compressions and rarefactions. All right, so in order for sound to travel, it has to have a medium. So that would mean that in space, sound will not travel because it's in a vacuum. So on the test that involves a space question, when one astronaut's talking to the other, don't do the calculations, say that there'd be no sound because it's a vacuum. In space, sound would not travel. It is a vacuum, so you need to have some form of medium, whether it's liquid, whether it's solid, whether it's air. You need to have some form of medium in order for that energy transfer to occur. So sound is a form of energy transfer. Your diaphragm compresses the air, so there's that energy given. Okay, our body chemistry energy is compressing the air, which is creating an energy transfer. Transferring energy created, and we create a vibration. That's what our throat's doing then. It creates a vibration in the air around us. So for the energy to travel, it requires a medium, and the medium will determine the speed of sound. Okay, why is that? Well, we know that from the kinetic molecular theory that solids are tightly packed. So this goes back to our third unit. Tightly packed, which have low energy. All right, they're not vibrating very fast. Gases, going to the other extreme, are I'll go loosely packed, even though they're kind of running around the room, but have high energy. So you have the two extremes here. So what basically happens is that sound will travel faster, okay, in a gas. Oops. Sorry, sound travels faster in a solid. That's because in order to do the energy transfer, think of it this way. The bucket transfer, or the water brigade, okay? Who's going to get the water quicker to the fire? Here's team 1, and here's the bucket. Okay, and team 1 is got enough people that they're standing side by side, and so on and so forth, all the way to the fire here. Team 2 has one individual, or maybe let's go with 2 individuals. So if buckets are continually flowing here, all right, team 2 represents our gases. All right, so team 2 is the gas team, whereas the solid team, you can see that the pail can pass much quicker when the people are tightly packed. They're able to get that pail down the line quick, whereas in number 2, these people are going to be running around, and that's what air and gas particles are doing because they have such high energy. They are bouncing into each other, running around, but that means it takes longer for that pail of water to get to that fire because they're running back and forth with the pails. So your solids will transfer sound much faster than the gases. So some examples of different mediums. So just to give you a feel for this, in our current textbook, it's page 446 where you'll see a list of them. But I want you to just pay attention to the categories here. So we have medium, we have density, and we have speed of sound. So air. Air has a density of about 1.29 and speed's about 331 meters per second. If you're underwater playing your stereo, water has a density of 1,000, but now the speed is almost 1,500 meters per second, and nearly 5 times faster. So people underwater will hear the music faster than people in the air. If we look at copper and iron, if you look at their densities, okay, copper has a density of 9,000, roughly, iron 8,000, but look at the speed difference here. Note the difference. So when we look at the density, copper is more dense, so that means the particles are more tightly packed. However, the speed is significantly less. So why is that? Why is there that difference between the two? Well, if you were to compare copper and iron, so if someone knew the difference between a copper pipe and an iron pipe, what could you tell me about the two? It's this statement right here. The stiffer the material, the faster the speed of sound. So stiffness is the major factor when it comes to speed. So stiffness of a material plays a larger role. Large role. Okay, so stiffness of a material trumps density. So general rule of thumb, the denser the material, the faster it goes. But stiffness is really your defining factor. So if you were able to visualize, or if you've seen it before, copper pipe versus an iron pipe is very, very tough to bend, where a copper pipe is more flexible, more malleable. You can actually twist it around. Okay? So even within air itself, there will be a variance of velocity. Okay, so now moving out of the solids, I'm just talking about the air around us. There's going to be a variance of velocity, as with all materials. As the temperature of the medium increases, so as the temperature of our air increases, the distance between particles increase, making the transmission of energy less efficient. And I don't like how that's worded now that I read that out loud, because it leads to the wrong conclusion here. So let's do a little bit of editing here. So as the temperature of a medium increases, the distance between particles, let's add in the distance and energy. Whereas increase making the transmission of energy, and that actually should be more efficient. Okay, and I'm not going to worry about the example, and we'll talk about that in a sec. So as the temperature increases, sound will travel faster, and it's because those particles are moving faster, moving with a higher degree of energy, so there's more collisions, which allow for the sound energy to be transferred faster than in slower moving particles. Okay, so to summarize this, temp of air increases, so does the velocity of sound. It too will increase. How will it increase, or what relationship? It's right here on the next part in your next slide. So through experimentation, physicists have determined that the temperature is a linear relationship. So they've plotted it, and they found that 0.6 meters per second per degree Celsius. So just cleaning up our formula, V is obviously velocity of sound. Maybe I shouldn't say obvious, but and T, and I don't understand why I used capital T there when I typed that up. You may want to edit that down. Well, I guess the problem is small t should be, that's temperature though, so I guess that's why I ended up using the larger T. Small t is more for time. So capital T for the temperature, and that's got to be in degrees Celsius. So the example here then, find the velocity of sound in air when the mean temperature, so just a fancy word for average, is 30 degrees Celsius. So you're just using the formula here. So there's going to be a lot of times where you got to do this calculation first before you can answer the actual problem. So as we go through, plug it into the calculator, you get 18, 2 plus 18. So 332 degree, or at 30 degrees Celsius, we find that the speed of sound is 350 meters per second. Compared to if it was at freezing, 0 degrees, it would be 332. So it definitely does increase as the temperature does. So at 30 degrees C, speed of sound is 350 meters per second. There we go. Let's do next example then. If you see lightning strike, and then 5 seconds later you hear thunder, how far away, how far from the lightning are you if the temperature is 18 degrees Celsius? So first thing we need to do, we need to calculate the velocity of air at that temperature. So using that formula, plus 0.6 times 18, so we can calculate the velocity of sound in air at that moment in time. Now, just going back to kinematics, since sound is not going to accelerate, okay, it's an energy source, it's a pulse that's been sent out, so travels at a constant velocity. We can calculate its distance from our kinematics formula. So we have our 342.8 multiplied by 5 seconds later, which would tell me that we're looking at 1,714 meters, or 1.7 kilometers. So therefore, the lightning strike was 1.7 kilometers away. So it seems like a natural stopping point here, and I'll finish up. I got a couple more examples. I want to talk about the Mach number, and fairly straightforward, won't take too long, and then we can move forward from there.